Swayam Prabha. Digital India. Educated India.
New lecture of fundamentals and applications of dielectric ceramics. So let's just briefly review the last lecture. So in the last lecture we talked about, we basically narrated the contents. So we looked at the contents of the course, and then we looked at the bibliography, the kind of books that you need to read, and then we introduced some concepts related to structure. So we started with the concept of lattice and unit cell. So basically we talked in the framework of point lattice. Okay, so what happens when you have points present in the space? So depending upon the arrangement of points in the space, you can construct a body which is called as point lattice, and within this point lattice you can construct a smallest repeatable unit which is named as unit cell. So basically a point lattice is a regular periodic arrangement of points in a space with identical neighborhood of points, and then you can put in you can construct a unit cell within the lattice which is a smallest possible repeated unit. So for example, if you have this kind of arrangement of points in a space, this is the simplest possible arrangement. So we are drawing this in 3D, but you can draw this in 2D as well. So the lattices that can be drawn, the unit cells that you can draw could be like this. So this is a repeatable unit. You can also draw this as a unit cell as well. This is also a repeatable unit, and mind you, all of these unit cells have lattice parameters which are the areas which are similar, and the number of lattice points. The number of lattice points is basically number of corners divided by 4. So you can see that each of these consists of one lattice point and they have similar area. So choice of unit cell is not unique. So basically the message was that choice of unit cell is not unique. You can make several shapes, and as a result there are various possible combinations. So the question is, how do you reduce the number of choices, or how do you put in a framework which allows you to simply distinguish between various shapes? And this is what is called as crystal systems, that will come to later on. Now when you have this, so now the second thing is what happens. So this is about the point lattice. So point lattice means construction of lattice with the use of points in space. Now the second thing which is called as motif. The second concept that you require is that of motif, and motif is nothing but an object or an atom or molecule, which could be group of atoms, and so on and so forth. So when these motif or units, they replace the points in the unit cell. So basically when you have, so it could be one atom, it could be group of atoms, 2 atoms, it could be something like this, and so on and so forth, and there is a possibility to make variety of shapes. So on this unit cell I can construct, using the first one, a unit cell like this, or I can have a unit cell in which I can put the atoms like this. So provided they are put in such a manner so that the neighborhood remains identical and the arrangement remains periodic, they will all make what we call as a lattice. So when you put this motif plus point lattice, then what we make is called as a crystal lattice. So basically a crystal lattice is nothing but a combination of point lattice and motif, which is in the case of solids nothing but atom or a group of atoms. So this motif is basically atom or a group of atoms. Okay. So one example, for details I would recommend that if you want to learn the details of this thing, then I would say you should look at the course on nature and properties of materials. and the videos are available on YouTube or MOOC site. So, this is nature and properties of materials, basically structure of materials, So, this is a course in which I have discussed what is the meaning of motif in a very detailed manner. So, for example, you can make a lattice, so I will just give you one example and rest you can do by yourself. So, let us say if I construct this kind of lattice and I have okay. So, this is just a monatomic lattice. Okay. In the monatomic lattice, so in this case the smallest repeatable unit is this, okay, and so a smallest repeatable unit is called as a primitive cell with one lattice point, okay, and then you can construct a non-primitive cell which is this cell, which is called as a non-primitive cell with two lattice points, okay. So, you can see that area of non-primitive cell is twice the area of primitive cell, okay. That is very obvious, and it contains two lattice points. So, it basically scales with the number of lattice points. Now, suppose in the similar cell, if I construct another similar cell and put in and then I put another atom here which is like this. So, now what happens is basically I can see that while this atom has a neighborhood which is made of these four. So, let us say this is A and this one is B, okay. So, B atom neighborhood is 4 A atoms, whereas neighborhood of A atoms is 4 B atoms. So, both of them have different neighborhoods. So, that is why they are not separate lattice points. So, what you have in this form now, your lattice is not just so this is, so if you now construct this as a lattice unit cell, this is not the smallest unit cell because you have different lattice points of different neighborhood of different points. Instead, the lattice now becomes this particular body which is repeatable in space. So, this is the smallest repeatable cell that we will make in this unit cell. So, this will be, and this will have one of A atom and one of B atom. As a result, the formula will be AB in this case. So, basically it is like saying I have a unit cell which consists of a molecule AB. So, you can keep the corners of this unit cell here, can consist of corners here or here. So, if you construct unit cell here, then basically what I am saying is that this dumbbell shaped molecule AB is the motif or the unit that is placed at the lattice point. So, this is the motif. So, motif in this case is A at, for the sake of simplicity you put the corner on one of the atom. So, A at 0 0 and B at half half, whereas in this case the motif would be, for this cell it would be primitive and this would be a primitive cell, okay. Whereas in this case the motif would be at A at 0 0 0, there is no B atom, it is just A atoms, all of them. So, if it is all of them A, then it's just, so if it is a primitive cell, then you have to define the position of both the atoms. But if you want to define non-primitive cell, let us say for this non-primitive cell, I say this is a non-primitive cell, let us say it is a centered cell. So, I define this as a centered cell, and in this case the motif would be, you can say A is equal to 0 or you can say A is equal to half half. So, the moment you say it is a centered cell, the motif at A is equal to 0 will automatically mean that you have 1 at 0 0 and 1 at half half, or if you say A is at half half, it would automatically mean that there is another one at 0 0, because the translation vector in this case is this translation vector. So, translation vector is the lattice translation vector is not in this case. In the case of compound, the lattice translation vector is not this, but this. This is not the lattice translation vector, this is lattice translation vector. So, you have to go from same atom to another atom to complete the lattice translation, and it should be repeatable in space. You can make it more complicated if you have asymmetric molecules and stuff like that, it becomes more complicated. So, for details I would say that you should go to the first the first module of nature and properties of materials course, that is structure of materials, and look at the first module based on structure. So, there I have discussed this concept of motif in detail. So, basically motif, or which is motif is also called as basis. So, motif or basis, when you combine it with the periodic point lattice, it makes what is called as a crystal lattice or crystal structure. So, as we saw that, so what do you know now? You know what is point lattice, you know what is unit cell and parameters. We also know what is motif, and we also know what is crystal lattice. Now, to distinguish between various shapes and possibilities, based on the symmetry arguments, people have evolved what we called as crystal systems. So, these had been put in the framework of it's called as a crystal system, because we have multiple choices of unit. Logical fashion, not to have millions of choices, we have defined a framework which is called as crystal system. So, based on this, people have defined various crystal systems, which are essentially it is a framework that allows one to put different shapes into certain categories which are well defined. And for this we take the help of symmetry. Now, for a lattice there are certain symmetry operations that one must be able to perform. What is symmetry? Symmetry is basically an operation which brings an object into self coincidence. Okay. So, let us say if I have this array of points in a space, okay, for array of points in a space, if these are all identical points, then this point is, and if you have this infinite array, let us say, then this point is identical to this point, if this point is identical to this point, provided they have this translation T which is similar. So, this is 1, 2, 3, 4, 5, 6, 7, 8. So, and so on and so forth. Okay. So, whether you are at 1, whether you are at 2 or 3 or 4 or 5 or 6, it does not matter, because the translation of all the points around is similar. As a result, this is called as translation symmetry. So, this is and this is a must have symmetry for any kind of object. Now, another thing that you can have here is, basically the idea is to bring the object into the self coincidence. So, there is a possibility that if you put in a mirror plane here, reflection, then 3 looks similar to 4. If you put a mirror plane here, then 4 will look similar to 5, or 6 will look similar to 3, and so on and so forth. So, you can have mirror plane and this is called as reflection symmetry or mirror symmetry. And the other symmetry operations that you can perform are, so this is about 1D, all right. Now in case of 2D, the number of symmetry, so if you have a 2D object like this, let's say, and if you go on like this, okay, so let's say these are 4 squares put in such a fashion so that this is A, this is A, this is 90 degree, all right. So we have translation symmetry whether you are at this point or this point or this point. So A, B, C, all these are identical points. So whether you are at this point A1, B1, C1 and so on and so forth, it does not matter because translation symmetry will permit you to have identical neighborhood at each point. So the translation is there. You have mirrors which are there. So if you draw a mirror which is, for example, at this position, then we have mirrors in this fashion, we have mirrors in this fashion also, and we have mirrors in this fashion also. So we have horizontal mirror, we have vertical mirror, and we have diagonal mirror. So we have translation as well as reflection symmetry. Now another thing that is possible is what will happen if you rotate it, for example, at this point by certain angle. So we can see that we can bring this object, if this is a square shaped body, we can bring this into self coincidence only if we rotate it by 90 degrees. If we rotate it by, so maximum angle by which we can, minimum angle by which we can rotate is 90 degree. Of course, if you rotate it by 360 degree, it will come into self coincidence. But what is the minimum angle by which you rotate it so that it comes into self coincidence? So minimum angle, minimum or smallest angle of rotation which will allow you to have self coincidence. So this is called as rotational symmetry. So in this case you can rotate it by 90 degrees, but how do you evolve a general framework? So in this case we define what we call as n-fold symmetry. And this n is the number of fold, or rather defines the angle of rotation. Okay. So n is equal to 1 will mean 360 degree rotation. Okay. So basically what it means is that it's a rotation by 2 pi divided by n. N is equal to 2 will mean 180 degree, which is basically 2 pi divided by 2. N is equal to 3 will mean you will have 2 pi divided by 3, that is 120 degrees rotation. And n is equal to 4 will mean 90 degrees. N is equal to 5 will mean 72 degrees, and n is equal to 6 will mean 60 degrees. So various possibilities are there. So for shapes like triangle, anything triangular will have 3-fold, a pentagonal thing will have 5-fold, then you have hexagonal things will have 6-fold, and rectangular objects will have 2-fold. So from the perspective of space filling without any gaps, 5-fold is not possible. So the only possible symmetries are 1-fold, 2-fold, 3-fold, 4-fold and 6-fold. And you can try this on various objects of different shapes and see which symmetries they follow. And finally, so this is something that you require. for a 2D object. For 1D object you are okay with only translation and reflection, but for 2D objects you require, in addition to translation reflection, you also require rotation symmetry. And for 3D objects one more thing is added, which is called as inversion symmetry. So inversion basically is in 3 dimensions. Let us say you have a body like this, so obviously this 3D object will have translation symmetry elements, reflection symmetry elements, and rotation symmetry elements, but in addition it will also have inversion. So for example, if it is a cube, then this point A1 can be brought into position A1 prime through a center of inversion which is located here. So this is center of inversion. So basically, in general terms, it means that anything which is at x, y, z, it can be seen or if it can be brought into self coincidence at minus x, minus y, minus z, then this is called as you are going through a process of inversion. So what we have seen is 4 symmetry elements: translation, reflection, rotation and inversion. So in 3D it is important to consider the inversion as well, whereas inversion is not considered for 2D objects. So for example, now let us look at the symmetry from the perspective of 3D objects. So we will just consider cube, for instance. If you have a cube, all right, and why I am focusing this a little bit, because when we learn about ferroelectricity we will need these concepts back on. So this is a cube, okay. So cube means A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree, okay. So in this cube you can see that faces of cube are squarish, so which means all of them can be rotated by 90 degrees. So all the faces have 4-fold symmetry elements. So cube has 6 4-fold symmetry elements along the rotations along face normals. You can also rotate cube along by 180 degree along these diagonals. So if you put diagonals like this, I will use a different color. So if you connect this point and this point, if you connect this point and this point to that point, so you will have these diagonals connecting each other. So 6. So how many of these will you have? You will have one of this, one of that, then one will connect here. So and then we will have, so 1, 2, 3, 4, and then we will have one of these, and then you will have one of these as well. So you will have 6 2-folds along face diagonals. And the third thing that cube must have, the defining symmetry of the cube, is the 3-fold rotation along this axis, which is the 3-fold along body diagonals. So in 3D case, the rotational symmetry often becomes the defining symmetry of 3D shapes. So for a cube, for example, it must have 3-fold along the body diagonals, 4 of them, okay. So based on these symmetry arguments and the lattice definitions, people have come up with the system of crystal framework, which is called as crystal system. So first of these is cubic, which means alpha is equal to beta is equal to gamma is equal to 90 degree, and A is equal to B is equal to C. That is what we have seen. If you distort it a little bit, you make a tetragonal system, which means alpha is equal to beta is equal to gamma is equal to 90 degrees, but A is equal to B is not equal to C. So, C parameter is little bit shorter or longer as compared to A or B. Third is called as orthorhombic, wherein alpha is equal to beta is equal to gamma is equal to 90 degree, but A is not equal to B is not equal to C. These three are basically orthogonal systems, but they have different symmetry elements. Defining symmetry for a cube will be 4 3-folds. For a tetragonal, you must have 1 4-fold. For orthorhombic, you must have 3 2-folds. These are the defining symmetry for these systems. And then, these are these 3 4-folds are, and these 3 2-folds are perpendicular to each other. Okay. And then you have non-orthogonal systems such as rhombohedral, for which alpha is equal to beta is equal to gamma is not equal to 90 degree, but A is equal to B is equal to C, and this must have 1 3-fold rotation in the system. That is a definition. Okay, 1 3-fold rotation. And then fifth one is hexagonal. Hexagonal is basically A is equal to B is not equal to C, and alpha is equal to beta is equal to 90 degree is not equal to gamma, which is equal to 120 degrees. Okay, and for this we must have 1 6-fold rotation. And then finally 2 more choices. Sixth one is called as monoclinic, for which A alpha is equal to gamma is equal to 90 degree is not equal to beta, and A is not equal to B is not equal to C. It must have 1 2-fold rotation axis. Okay, so, and then seventh is triclinic, for which alpha is equal to is not equal to beta is not equal to gamma is not equal to 90 degrees, and A is not equal to B is not equal to C, and it does not have any symmetry element. So, these are the classifications which have been made on the basis of symmetry. So, you do not have, although you have infinite choices of shapes, these are categorized in these 7 categories of crystal systems, which makes it easier to classify different solids in easy to understand categories which are based on symmetry arguments. You will have a cube only when it has a 4 3-fold axis. You will have a tetragonal crystallographically only when it has at least one 4-fold axis, and so on and so forth. So, we will stop here today. In the next lecture, we will talk more details of structures of dielectric ceramic materials. Thank you very much.